Morning. I got Mike a few emails because now the microphone is on. So welcome. Today, as promised, we're going to talk more about multivariate models. Basically, we're going to spend quite a bit of time on a package in R called Marima, but we'll also spend some time on another example trying to solve it in other ways, because last time we pretty much just said this is a framework, but we didn't quite get to the point of estimating parameters. And if you have a class of models and you don't know how to estimate parameters, well, from a statistical point of view, it's not so interesting. So that's the main target. I gave you the reference for the original paper by Henrik Splid, who is, well, now retired as a professor here, who made this algorithm. And I don't know how many of you have looked at it. I have. Very few of you. I won't go through the detailed calculations. I asked Henrik about it someday, and he actually couldn't repeat it if he had to do it just today. I mean, it will take some preparations, because some of those things are not things that you do every day. So have it there, as that is actually what's going on underneath the hood. What I want to do and spend time on today is basically going through an example where we kind of discuss the features of the package without going too much into detail with what happens in the estimation as such. Basically, the estimation is a linear regression model that is fitted. But I'll also mention that later on, slightly how it works, but not exactly how it works. The trick is, how do you make an ARMA model a linear regression model? That's effectively what is being done. So I'll swap. At some point, it will be good to have both slides here active. So this here is, you can say, it's last year's version. There's an updated, the package in CRAN is updated, and there are some minor details that are changed, but you may not notice it. So first, I'll just spend some time walking through the example, have the index, spend enough time on that. Well, maybe just to say, It's also a recap of what is an armor model, and also how to organize things. A little bit about differencing, and this is kind of long-term lagging. It's not something you may have to do, but it's just a totally different way of doing it now that we have it as a multivariate series. And a little bit about model selection, and then the main part is actually an example where we do this, first repeat what someone else did, and then expanding from there. So in Marima, the main difference from what you're used to, well, rather than x, it's y as the state. That should probably not be a huge difference. X or y, you're used to that. The main difference is that the noise are called u as an input. And it is, you can say, as an input as well, but we would typically use epsilon for noise, but whenever you see a u here, don't think of input, think of noise. So basically, we have the standard Arima model right here. And if u is defined up here and y, then we have a vector process or multivariate process. That's why Marima is multivariate. You will sometimes see multivariate, sometimes vector for ARMA or AR or whatever. Same thing, just different choice of words. And then, of course, the coefficients here are matrices. So that's the basic definition. Nothing changed there. How things are organized, that's a little bit different, because you're supposed to have that each column of the data in Y is one observation. Where usually you would have, you would say everything that is at the same time, you'd have that as a row. But in Marima, it has to be every column. If you give it something where you have more rows than column, Marima will just transpose it. So it will do it if you did not do it right. The reason why it is like that, I'll say it's partly for historical reasons, but it's the access time to memory. Because a matrix is not stored as a matrix in memory, it stores as one long vector, and the elements in R that you get, those are the column-wise elements. So the second element in that vector is the second row, first column, and so forth. Say if you have 7 states as we have here, then you have to go to the 8th element to go to the second column, the first row. Why is that important? Well, then it depends on how the computer and the CPU is actually catching memory. If you're using the elements that you actually have already, neighboring elements, they will be in the cache, so they're ready. You don't have to wait until you get the value from the RAM. That's kind of a high-performance computing issue, but that is the motivation here. It's sort of the same, in the line, the same thing that in MATLAB, if you do things as a for loop, and you can also do the same thing as a vectorized operation, it's much faster. It's sort of the same things, having less access to memory, and you keep more things in cache. And it used to be that the actual calculation part was happening in some Fortran code underneath, but now, and therefore it was important to have everything next to each other. Now it's all done in R. So it's not as important, but it's still more efficient. And well, we'll have the usual definition of operator polynomials. Just the only thing that is different from the notation in the Henrik Madsen book is that the matrices here, they are shown in the same with a lowercase phi and theta rather than an uppercase phi and theta that are used in the book. But today, everything will be matrices. So you should not be too disturbed by that. But those, I think, are the differences in notation that we'll meet. We use the backward shift operator to the pth and q power, and then we'll just take it from there. with this notation here, one thing is that is mentioned repeatedly throughout this document as well, is that you always have a leading identity matrix here. We talked a little bit, or at least I mentioned it last week, that you would have that leading identity matrix. Here you needed to say yt, it depends on the previous y's, and the epsilon t also goes directly in. You can create the noise. If you have that noise, you want to have it correlated, you do that by creating, where is that matrix? Well, it was on the previous slide. The sigma matrix out here, which is the covariance matrix of the noise. That's how you create correlation in the noise structure. Okay. Then there's another thing about mean values. What happens if you do not subtract a mean value from the entire data set up front and leave it in there? What happens to the model parameters? You have different representations of the mean up here, either as an eta or as a mu, related to how the phi operator is working on that. I won't get into details, but just so that you kind of aware that depending on how you deal with the mean value, you can get different values. In the case where you had in assignment 2 with the university activities, you were told what the mean value was, so you could just subtract that and then work with that. But you could also just work through it without subtracting it, and then you would get a different value that you have to subtract at some point. That's basically what is written up here. So what is probably more important is the ability to invert a matrix polynomial. We have done it for, you say, univariate series. When we looked at stability and invertibility, we looked at whether we could invert these matrices, these polynomials. And in a multivariate setting, it's effectively the same thing that we're doing. We want to solve this equation, basically. So we want to find which inverse operator. The inverse of phi is the one, of phi of b is the one that you can pre-calculate on phi of b to get the identity matrix. That all makes sense, right? But let's say that this is an AR2 process. So you have a second order polynomial. Phi of b is a second order polynomial. What is the order of phi inverse? The answer is the same if phi is an AR1 model, which you can do by hand. Yes, infinite. It's an infinite sequence. However, if the process is stationary, after some part of the sequence, it's virtually null. It goes to zero sufficiently fast, as we discussed many times. For the autocorrelation, it's effectively the same thing. And so after some lag, it is effectively zero. And here you can say you have to kind of measure the differences relative to the noise that we're applying. But that's the one thing. We will not be able to work in a computer with an infinite polynomial. So we will work with a finite, but we will be able to choose to what order do we calculate this. Sort of the same thing when you wanted to look at uncertainties related to AR processes. You only had to do it to find the first coefficient in a psi polynomial up to the order of your prediction horizon -1. So basically, you can take any model and write it like this. y equals a multiplication of the inverse of the AR part on the moving average part, and then just have it as a psi polynomial. This is also, you can say, the transfer function concept that we talked about the last couple of weeks, and here it's called the random shock form. So it's just a different word for the random shock is like sending a 1 through the system as we did last week. Basically, that is what is meant by the random shock. It's just a different word for the same thing. So these polynomials in R, how do we deal with those? Now, say if you have an AR2 process, what do you need to keep track of? If it is a three-dimensional process, you need the identity matrix, and then you need two matrices of coefficients. And the way they are stored is, well, it's not so clear from what is written. You have to read the entire text, and it makes perfect sense. If the order k is 3, you make an array with dimension 3, 3, and then the order plus 1. The plus 1 is to have the identity matrix up front. So you host the identity matrix, and then the following matrices are the coefficients. What? Okay, this is weird. Somehow I can only show one page here. I have it on that stick here, first page. Now this keyboard does not have a page down key. We'll try again. Okay, so what I wanted to do was just to kind of say, what does this look like? Just to create it. So for a third-dimensional system, it doesn't matter the arrow down there, and I want a second-order model, I will kind of just give it some names. So I have the dependent variable with what comes out, and the regression is what comes in, because effectively what we're doing underneath the hood is a lot of regressions. And the order has, so these are just names that we're going to use for dimension names. It might be nicer if I add a 0 here to not have, oops. Then there's no space in between. That's just the only difference. So this is the structure that we're looking at. Right now, I just fill in some NAs. So we have, this should be identity matrix, the first lag 1 coefficient and lag 2 coefficient. I could have just put some random numbers in, but for now it's just to give you, this is the structure that we have. So to do the inverse operator, there is a polynomial inverse operator defined, pol.env, and what you do is that you give it an argument L, which is to what lag do we actually want to calculate this. And that's basically what it does. Just gives you the first L coefficients in the inverse polynomial, which will then have a leading unity identity matrix, so it will have order k by L plus 1. So there's always this order plus 1 concept everywhere. If you forget to have the leading identity matrix, Marema is checking for that all the time, and if it's not there, it's added. But I mean, you might as well just add it originally. And if you use the built-in functions that we'll get to later, how to specify the type of polynomial that you're looking at, you will get those without asking for them. So it's not a big thing. It's just a matter of you have to keep track of the fact that you always have an extra matrix, an extra dimension. Sorry, an extra element than what you would expect, not an extra dimension. It's a third dimension. Almost everything are three-dimensional arrays, where the third dimension is the different coefficient matrices. And of course, if you can invert matrices, these polynomials, you also have to be able to multiply them. So there's also a function called pol.mul, polynomial multiplication. So it's not that difficult. There should be an example here on the next page, which I will just... presentation mode is bad for copying. So if I just copy this over here, I will just generate some random numbers as in without a leading identity matrix at first. If I take this polynomial, it looks like this, just some random coefficients. Maybe not an appropriate choice, but just to demonstrate what it does. I'll take this and I will invert it, only keeping the first 5 elements. So I get here, and you'll notice that the first matrix here, the first element in the third dimension, is the identity matrix that now popped up. Now, what I will do, just to see if everything worked out, I will multiply the inverted, I'll pre-multiply that on the original phi, and also keep the first 5. And if I look at this, well, I get the identity matrix at the first element. I should always expect to have that. But what is interesting is, what do I get for the following elements? What should I get? What should I get if I take phi inverse pre-multiplied on phi? So I should only get the identity matrix. So the second lag, which is then the first lag coefficient, it is indeed when the numerical precision just zeros. Same thing with the third lag. When we get to the fourth lag, we get some numbers that are 10 to the minus 16, virtually 0. And get to the fifth element, again we have some 10 to the minus 16. And when we get to the last element, because we only wanted it, the first 5 elements plus the identity matrix, now we're down to 10 to the minus 15. So we're quite close to 0. So for practical purposes, I mean, we got an identity matrix and 5 matrices with just zeros. So even though we only kept the first 5 elements in the inverse polynomial, if you want to make sure you get something that is stable to a higher order, I mean, you just need to include some more elements. And it's fairly quick to do. It's not that, it's just saying that you actually don't have to go to infinity to make it work reasonably well. The rest here is pretty much just to look at the effective order of this polynomial when I only keep track of numbers that are greater than 10 to the minus 12. And then it's a zero-order polynomial, as in it's just the identity matrix. So I can say I only want the first element, and that's what I get. But now we just looked at what was underneath. So this is just a helping function if you want to kind of trim to just remove lags that only contains if things that are virtually zero. So that was just something. And why do I spend time on doing things like this that are most of the time just happening underneath the hood? You'll understand that later, I hope. So another concept, I should go back full screen, is differencing. This is quite different in Marima from what you're used to, because basically what you're used to is to just do, you can say in a univariate time series, you just do differencing of some lag, like 1 or like season, 5, 10, whatever you like. But now for a multivariate series, what is the obvious pick? You can do, as is done right here, just take and do the same thing in a multivariate setting. So everywhere you had a B, when you have a 1, you have the identity matrix. And when you have a B, you just put the identity matrix in front. So this means that you take all variables, in this case 2, and you make a first order difference. That's perfectly fine. And the inverse operator of this operator is, as we saw now a long time ago, is the infinite sum operator. Again, this is just, and here you need a lot of terms to actually do it, because this up here is non-stationary. So you need everything. So if you want to difference twice with order 1, as in having in a Riemann model to just have lowercase d equals to 2, basically what you do is that you get yt minus 2yt minus 1 plus yt minus 2. So it's to get the curvature, local curvature, by multiplying 1 minus b, take that square, and evaluating that. So this you would want to be able to do. But you would probably also want to be able to do seasonal differencing. Just like we did previously, well, you could just take b to the seasonal power. So this is all the things that we're used to, where we just say, well, we'll just use the identity operator everywhere, so all states are treated the same way. But it might be that you have a model where this is not what you want to do. That's the seasonal operator, like this. But it might be that you want to have one variable with one season, another variable with a different season. Or one variable that you do not difference, another one that you difference. Depends on what you're looking at. Looking at the houses pricing, and you could say, well, what was driving that from an economic perspective? What you look at is the so-called log returns. That's the thing I mentioned in one of the following slides, lectures. So you take the price at 1 month divided by the previous price, and you take the logarithm of that, divided by the previous, so that's actually a seasonal, that's a lag 1 difference of the log transformed data. Now, previously for the 4th assignment, I won't give you this time, you had to predict a multivariate series of housing prices, and then you had to use interest rates as predictors. Because you can say it's the interest rate that determines how much you can pay right now. If you have the fixed income that you can use for buying a house or something, basically if the interest rate is high, you can pay less because you're paying more in interest. Whereas currently the interest rate is low, so you can pay more for the same amount of money that you pay every month, you can pay a higher price for the house. Could you actually model that and see that? That was basically it. But then you want to look at the actual interest rate and the different log prices. You can do that. So that's basically the definition. And then you have to figure out how do you make an interface that can do this. So this is done in something in a little bit. At first it looked odd, but it's very flexible way. And that's probably why it was chosen the way it is. So what you have to do, if you want to take the first state and difference it twice, and the second state, you want to make it a seasonal difference of lag 12. Then you have to give a matrix like this as argument, where the first rows are which states are you differencing, and the second row is to what lag. So you take the first state differencing with lag 1, then you again take the first state and differencing with lag 1, and take the second state and difference with lag 12. I see some eyebrows here that are. Yes, that is the same as, I'll show you in a moment, but that's the same as setting d equal 2. If you do it twice, you get the same as you first do it once. I mean, you take the difference operator and square that. That's the same as doing it twice. So if you do it the way we discussed it earlier on, this is d equals 2. But this is the same as nabla. That's basically saying doing it twice. Because this is just a multiplication, right? Is it clear? Yep. Good. Because it's important that you can see that it actually gives you the same thing. And you could have added, you can say, rather than this, you can add a third line and say, how many times do you want to do this? But instead here you said, well, if you want to do things twice, you have to write it twice. Because typically, as we discussed earlier, you difference, most often you just difference once and occasionally do it twice. So we want to make something where it's easy to difference once, and it doesn't have to be complicated to do it twice, but it should not be complicated when you want to difference just once. Yes?
Then why is it 1, 1, 1, 1, and not 1, 2? First element difference once again, but the second element you can difference 12 times.
Not element, but state.
Okay.
I think it's more clear if you look at it this way, because this is what comes out in the end. Actually, I would prefer to write it in a slightly different way than what is written there. Because this is what comes out in the end. And what you can see isn't that there? No? Basically, what we want to do, what you should notice is, where do we have, here you only have something in the 1,1 element. And that's the important part. So if we go back and say the 1,1 part there, what does that actually do? That corresponds to multiplying with, of course you need an identity matrix, and then a matrix where you have 1, 0, 0, 0, B. That is the operator. At 1, 1, we take state 1 and we difference it with lag 1, so that gives us this one there. And basically, the example from above, well, that is taking if you do it then a 1, 1, then you just take this and multiply with the same thing, the identity matrix minus 1, 0, 0, 0, B. If you multiply those two out, you get exactly the first 3 elements here. And then the last one was a 2 and a 12. Then you take the identity matrix minus, and then the only difference is then you take the second element in the diagonal and make that a 1, and everything else is 0. And then you multiply this on B to the 12th power. So that's how you construct them effectively. And if you just multiply these out, keep track of the order, and you get that. Is that clear to everyone? Because that's... Yes?
In the normal ARIMA models that we've been using,
Yes?
which version of notation do they then use? Do they use the where you get the when you difference, you get the polynomial of all the orders up to the number you write, or is it just the lag? Like if I use an ARIMA and I use the difference in parameter of 2,
Yes?
do I get for both lag 1 and 2, or just for lag 2?
You only get lag 2, but I mean, effectively, that's also when you multiply these two together, you also get lag 2. No, not lag 2, sorry. Yes, sorry, yes, you get... Now I hear what you're saying. What you're asking is, why do I have this lag 2 here, basically, right? Is that what you're asking?
No, actually it's the lag 1 that...
This one there?
In a way, yeah.
Yeah, but let's just do it.
No, I see, but I'm just wondering...
Yeah, but what does it mean? If you just do this in a univariate setting, this is 1 minus b times 1 minus b yt. So what do you get? You get the 1 minus 2b plus b squared on yt. So that is the exact same operator that you will end up having in the traditional ARIMA model. You just typically don't think of it as something that becomes a second order thing. That's why I said that this today is also a little bit of a recap. Okay, so this is, you can say, the combined polynomial that you get out. And if you transform the data with this, then you get a different series. And there is a defined diff function where you, well, that's what is the code that's written up there, where what you get out is the difference y from here. So you can use the difference y in your model instead of just the y. So in ARIMA, in the univariate case, you can specify the differencing operators in your modeling arguments. Here you actually have to do the differencing on your own before giving it to ARIMA. So that is yet another difference. But after the fact, you can take the resulting AR polynomial that you get from ARIMA. So if this, we'll label this here, as is given there. We'll just label this nabla of B. Then if you estimate a model to what was, you can say, if you define, say, we define set as nabla of B on yt, define set t as that. If you then fit a ARIMA model to this, that gives us an AR part. Just like in the univariate case, we get an AR polynomial that is made on set, but that's the same as what we have over here. nav log b on yt, and that equal to some theta polynomial if you have an MA part as well, on, now I'll write epsilon t as I usually do. But then we can just multiply these two polynomials together. And then we can use this polynomial when we're going to be making predictions. Because then we're back on the original scale. So that's where you're going to use the polynomial multiplier if you're going to do differencing. Okay. A lot of these things will be more clear when we go to an example, I think. But now I pretty much get through saying most things. If you have something where you have a long-term lagging, say lag 24 hours or something like that, then you don't want to have that huge a model. What you can do is to add an extra state that is a seasonal lag state. So you add not the 24, but the 23. And why that? Well, you have a yt, but when you use it, you look at how does yt, in the simple case, you just have some matrix here on yt minus 1. And you want out here to have the dependence on the one that is lagged 24 lags, but what you get is already a lag 1, so you should only do the lag s minus 1 lag operator up here. That's kind of a teasing part, I would say, in doing this. If you're just doing it with operators like this, you don't have to pay attention. It happens automatically. But if you want to add them as an extra state, you have to keep track of what is actually the lag that you're looking at. So the model you're doing here is basically to say that for the third variable here, you don't make any model for that. You just store that. But that's just one way of doing this, if you are going to need to do this. There's also, to create this, you don't have to do it all by yourself. There's a function called season.lagging. And I'll just go quickly over this. So if you want to take the first variable, create a third variable with lag 5, take the second variable, create a fourth variable with that, and make it lag 11, or effectively 6 and 12. So this would give you what you could use to make a seasonal model of order 2 with season 6, for instance. I don't know if you can see that. But basically what you get out are some lag 6 and lag 12 states, and then when you multiply that on matrices, you get it as a lag 6 and a lag 12, which is a second order polynomial in lag 6, because you have both the 6 and the 12. But you have to keep track of what you want to be doing in those cases. It's not just straightforward. What the seasonal lag function is doing, if you create this lag matrix, is that it takes the original data and then it creates the lag data where it pads with some NAs where you don't have anything, because you just shift the data, so you're lagging the first 5 here and the first 10 there, or 11. Likewise, in the end, this will become longer, because you'll shift everything out to n here, so I'll have some gaps up here. There'll also be some gaps there. So just so that what you get out of this function, if you're going to use it, you probably want to spend a little bit more time on doing it. But now it's just basically just to mention that you can there's a function that can help you creating these lag variables. And if you need it, spend time doing it. So now we get down to the important part, I would say. Define.model. So far we just looked at how to handle things around, but what we want to care is how do we specify the model that we want to estimate. At the end of the day, that is what we want to do. So I'll give an example in a moment where we'll do these things. Basically, it's using the linear regression model repeatedly internally. Doing the inversion to polynomial and expanding everything out, then it can be done as a lot of linear regressions. That is what's given in the paper that I gave you the reference for. I won't show it, I won't scare anyone. But I would say what I ask you to read and look at is just a bit over a page or so. So I would recommend that you just download it and just read through it. And it's okay if you don't understand, but just to get a grasp of what is actually happening. Get to talk more about penalty in a moment during the example, because basically what we do here is just to estimate all parameters. At some point, we also need to figure out which parameters are actually significant. Basically, what we get out as outcome, we get some f values, and then it will trim those out that are less than a given penalty. The AIC criteria corresponds to having a penalty of 2. Typically, F-test corresponds to having a penalty of 3.84. We'll see what matters in the example. And the example comes now, but I think we should have a break and start just 5 minutes to 9 before going through this, because otherwise it will be too long.